Hi everyone, welcome to my channel and welcome to this video. In my last video, I spoke about a socket option called SODUs port, and what we discussed is that how SODUs port can help us make multiple processes listen on the same IP and port combination on the server, or rather on any machine. So what happens is that whenever we send traffic or connections to that particular IP and port, the data or the connections get distributed quite fairly among all the processes that's listening on that same IP port combination using SODUs port option, right? And we also discussed how it can help us with hitless reload and out of the box traffic balancing, like out of the box traffic load balancing between multiple processes and things like that. So now I have another question for you all. So let's say I have a network, a local network, or maybe a network of network. That's irrelevant for now, but let's say we have a network and where we have got multiple hosts, and let's say there are multiple processes maybe on the same host or on different hosts in the same network, all connected to the same router, and they're all listening at some IP port combination on various hosts. Need not be the same IP port. If it's a same machine, then maybe on the same IP port or different IP port, doesn't matter. But the point is that there are multiple hosts ready to receive traffic on multiple hosts or the same host in the same network. And now what you have to do is you have to send data, like the same data packet or datagram, to all these hosts at the same time, right? So now I'm no more talking about distribution, load distribution or anything like that. It's a very simple ask. I have some data or some packet that I want to send to all the hosts, all the interested hosts which are interested in receiving that packet. I want to send that packet to all those hosts simultaneously at the same time. That's the thing I want to do. Now, of course, one very simple thing I can do is that from the client who wants to send this data to all the hosts, one thing that the client can do is create multiple TCP connections to all the, let's say there are 5 hosts or 5 processes to which I want to send this packet. What I can do is I can create individual TCP connections to all these 5 hosts and then send the same data 5 times in an iterative way, one by one, or maybe I can spawn 5 different processes each for one of the hosts, and I can send those data, right? So that's one way I can do it. So I can create multiple individual connections, or if I'm using a connectionless protocol like UDP, I can simply send these packets to individually to all the n number of hosts or processes to which I want to send this packet. Now just think about this. So if you are trying to send this data to these multiple hosts in the same network, I mean to the hosts that are interested in receiving this data, if you are trying to send this data to all those hosts in the network individually by creating individual connections to these hosts, just imagine the amount of bandwidth you are wasting. At the end of the day, same datagram or is the same packet, yet you are creating individual connections and sending them multiple times. So you are pretty much using up the bandwidth way more than what is required in reality, right? But because the data is same, it's not that you are sending different data or different packets. It's the same packet. So what's the way forward? Like how can you send once, like you send a given packet once, but all the hosts or rather all the processes that's interested in receiving the data that you are sending gets the data at once, right? The client who is sending this data doesn't have to send it individually to all the hosts multiple times, right? It doesn't have to do that either iteratively or concurrently for all the hosts, but it just sends once and all the hosts receives the data. How can you achieve this? This is what we'll be discussing today, and this is a very interesting thing in computer networking. This concept of one client or one computer, one network node sending data to another node, a server or another peer, by creating a connection with that peer, like only one peer. It's something called unicasting, right? It's called unicasting because sender is only a single entity and the destination is also a single entity, right? And in unicasting, even if you want to send the same packet to multiple hosts, you need to create multiple connections to each individual host, right? If it's a connection based protocol like TCP, and if it's a UDP, then you need to send the same packet again and again to the different hosts to which you want to send these packets. So that's unicasting. Obviously this doesn't solve our purpose. What we want to do is we want to send once and make it receive to all the hosts, all the interested hosts. And for this purpose, we have got 2 protocols that can achieve this for us. And those 2 protocols or those 2 approaches are multicasting and broadcasting, right? So we'll be discussing about multicasting in this video and how we can use multicasting to achieve our purpose. That is, the client will send once and all the interested hosts in the network will get the packet, will get the data. So the word interested is very important here, right? So that the word interested is one of the factors that differentiates multicasting from broadcasting. So yeah, we'll discuss in details about multicasting. And not only that, we will actually write a server and client, then we will spawn multiple versions of that server. By server here I mean the process which is at the receiving end of the data. I will spin up multiple such server programs or such processes which will be listening on the host, and then from the client I will send the required data only once, and all the different processes should get that data all at once, right? The reason I'm saying process, the reason I'm differentiating between process and host so many times is that since I'll be trying out in my own local machine in this case, and I really won't be using multiple hosts but rather a single host, so I will be kind of simulating host by creating multiple processes on the same machine, right? For the hands-on example that I'll be showing you all, I'll be using multiple processes, right? And I'll be using multiple processes on the same host that will be interested in receiving that data from the client, and the client will also be on the same machine, and the end result should be the client should send out the data once, and all the interested processes running in the machine should all get them at the same time. Had I attached another host to this network and run the same server in that host as well, same server process on that host as well, connected to my same home router, that it wouldn't have been anything different, right? That host would also receive the same packet. So it's not that something different is going on just because I'm using multiple processes in the same host and not just multiple hosts, but the end result will be same. But just for simplicity and ease of the process, I'll spawn multiple processes in the same host. So yeah, that's what we are going to discuss today, and that's what we are going to do today in this video. As always, without further delay, let's get started. Okay, so now let's try to understand what's the primary difference between unicasting, multicasting and broadcasting, and then we will look into multicasting in details, right? And we also need to understand why we can't use broadcasting in all the cases and why we need multicasting. So the most common way of sending data from one node to another is unicasting, right? And unicasting is largely the approach followed by nodes in the internet, because unicasting solves most of our purposes, right? It solves most of our problems. It's only certain very important cases which unicast cannot solve. For example, streaming is one such example where a streaming server needs to stream particular content to multiple nodes. There you don't want to stream the same thing again and again to different hosts, like individually to all the hosts. But anyways, we'll come to those things later. But let's look at unicast. So unicast is the simplest of all. Like you have a node n1, another node n2. Now n1 can be client or server, n2 can be client or server. Basically n1 and n2 are peers of each other, right? So let's go with TCP first. So in order to send, let's say n1 wants to send some data to n2, and for this example let's say that a process is listening at a particular IP I and port P. And so now let's say n1 wants to send some data to I.P. If it's using TCP, it will first create a connection with TCP. It will send the SYN, it will get back SYN ACK, and it will send ACK. And once the connection has been established, it will start sending the actual data. And once n2 will get the data, it will send an ACK. Again, if n2 wants, it can send some response back to n1, and so on and so forth. And in this case, the thing we need to understand here is every TCP connection needs at least 4 things. The 4 value tuple is what defines the TCP connection as source IP, source port, and destination IP, destination port. So these 4 things is must for a TCP connection. And one cannot create simultaneous TCP connection to multiple hosts, let's say. So again, it's not a direct connection. Let's say in between there is it can be a direct connection, but but let's say there is what I'll do is, let's say there is a router here R, and basically both n1 and n2 are connected to these routers, and that's how it's via this router that's n1 is sending packet to or data to n2, right? So at a time n1 can create one TCP connection to n2. By at a time I means like using one socket, it can only connect to n2 or any other host, right? Let's say there are 2 more hosts like n3 and 4, all running some server process, like any process listening at a particular IP port. Let's say this is I1 P1, I2 P2, and I3 P3. Now N1 cannot have a single socket which is connecting to N2, N3 and N4. That's not how TCP works. What N1 can do in this case is, if N1 wants to send the same packet to all the three other hosts, N1 has to do three individual independent unicasts, right? N1 can create a connection to N2, N1 can create a connection to N4, N1 can create a connection to N3. So there is no avoiding this. You do multiprocessing, you do whatever you want, like multiprocessing, multi-threading. You have to send the data three times. By sending data, I mean from the outgoing interface of this, like from the network interface of NI, let's call it IF interface, the network interface. No matter what you do in case of Unicast, three times the same data will be sent out to the three different hosts. So there is no saving from this. So even for the same data, you are using three times the bandwidth, right? Now coming to broadcast. So what broadcast does is, let's say there is a router R and there are nodes N1, N2, N3 and N4 connected to this router, and let's say the address of the network is something like 192.168.20.1. so that is the IP of the router, and N1 is, let's say, 192.168.20.2. this is dot 3, sorry, this is this is dot 2, this is dot 3, this is dot 4, and this is dot 5, right? Okay, so now let's say N1 wants to send the same packet to all the four hosts, like all the hosts in this network. Like in this case we have four hosts, but we are talking about all the hosts. If N5 was also there, let's say N1 wants to send the data to N5 as well. And that's the most important, like that's one of the most important distinctions between broadcast and multicast. In this case, broadcast comes into picture only when N1 wants to send data to all the hosts present in the network. So in that case, what N1 can do is N1 can send the packet not to any particular IP but to a special IP. Okay, so before that, let's consider there is a /24 subnet network, right? Which means that you can only use the last 8 bits or the last octet of this address of this IP to denote a host address, right? Okay, so if now anyone wants to send this data to all the hosts present in this /24 network, subnet network, again, it is just for example, it can be any, the subnet mask can be anything, the approach remains the same, right? So it can send, N1 can send the data to a special IP. Like in order to send it to all the hosts, it can send it to a special IP which is 192.168.20.255. How I got this? I got this by leaving aside all the bits reserved for the network ID of the network address, and I just flipped all the, like, and I made all the remaining bits as 1. So basically what I did is if you convert this address, if you convert this network address into this, even this address, like if you convert 192.168.20.2 into its binary, right, and you AND it with the binary of the subnet mask, which in this case for a /24 network, the subnet mask would be pretty much 255.255.255.0, and you bitwise AND these two things, the result that you get is pretty much the network address, and then what you need to do is simply flip all the zeros to 1 and you will get this address, right? And this is called the broadcast address of this network. So if N1 sends anything to this address, it goes to all the hosts if they are listening at the broadcast IP. So if N1 sends the packet, the UDP datagram, to this IP, that is 192.168.20.255, all the hosts in the, of course it needs to specify a particular port on which all the processes on all the hosts are listening on. So if the datagram is sent on this broadcast IP, the datagram would reach all the hosts in the network. So all the hosts would get the same datagram that N1 sent out, right? So in this case, again, note the difference is N1 is no more doing in this case N1 is no more creating individual connections to N2, N3 and N4, right? It's not doing that. What it's actually doing is it's simply using the broadcast address, sending the datagram on the broadcast address, and whenever you send something on the broadcast address, all the host IPs present on that particular network will get that packet. And now if something is running on that particular port of that IP, they will get that packet, right? In this case, N2, N3 and 4 are running at 192.168.20.3, 4 and 5 respectively. If they have something running at the particular port of their choice, which N1 already knows, if something is running on that particular port on which N1 sent the datagram, they will get it. That's an overview of broadcast. But there is a problem with this. Like for example, let's consider there is another node n5, right, and another node, let's say n6. So now there are total six nodes in the network, but now there is an issue with this method. I won't call it a issue or a problem, but it's simply how UDP broadcast works. Couple of use cases that UDP broadcast won't solve, or some of the problems that UDP broadcast won't solve, is what if N1, like the node which is transmitting the message, it doesn't want the message to be transmitted to all the nodes present in the network, or rather all the host IPs present in the network. Let's say N1 wants to send that message or that datagram to only N2 and N3, but not N4, N5 and N6. What would N1 do then? With UDP broadcast, N1 doesn't have that control. Like whatever N1 broadcasts as a UDP broadcast, all the hosts or all the host IPs present in that network will get that data. So let's say if N1 doesn't want the datagram to be sent to N4, N5 and N6, it cannot do that, right? Unwantedly it will be sending to all the hosts if it's using UDP broadcast. And now think this from the perspective of the client or the other nodes or any node in the network. It might not be interested in certain messages that N1 is sending for all the hosts, right? So for example, even if N1 is fine with doing a UDP network UDP broadcast, like a network all hosts level broadcast, maybe that broadcast has got some value for N2 and N3, but N4, N5 and N6, let's say that broadcast message or that broadcast datagram has no value. So but even then N4, N5 and N6 doesn't have any other choice but to accept that broadcast. Or one thing that N4, N5 and N6 can do is at the application layer, it can check the data, some marker in the data, and decide, oh okay, it's not for me, and they can discard it, right? But even then it has to do some logic at its end to understand what's necessary and what's not necessary, what's the actual needed datagram and what's a unwanted datagram, right? So that's a manual thing that the that N4, N5 and N6 would have to do. And this is where multicast comes into picture. How multicast works is it allows you to create certain groups, right? And you can let hosts subscribe to those groups, right? They can subscribe to those groups, and all those groups has something called a group IP address. And whenever N1 sends a datagram to that particular group IP address, the router to which all the hosts are connected makes sure that only those hosts which have subscribed to that particular group IP address, only they get the datagram. Not everyone gets the datagram, right? It might sound a bit complicated, but it's pretty easy and pretty simple, at least at this level. So let me just make some space and I'll just reiterate over what I just said. Okay, so multicasting, it introduces the concept of groups or groups of IPs or groups of hosts, right? If I consider an IP as a host. In the multicasting world, if I ever refer to something called a multicast IP, I'm not referring to a particular node or a particular host, but I'm referring to a group of hosts. Now that group of hosts can have a single host or no host at all. That's a separate thing altogether. But a multicast IP is not attached to any single host, but it's a logical entity. It's a logical group of hosts. So, and these are not just any random IPs, but in the classical way of grouping IP addresses, the class D address, I'm not talking about CIDR, but I'm talking about the IP classes. The class D group of IP addresses are reserved for multicasting. So how a class D address is, basically what makes a IP address a class D IP address is in the octet. Like let's say we know that there are 4 octets of IP address, right? The first octet should start with 1110, and after that, whatever it can be, like it can be remaining bits can follow their own particular order, but remaining bits can have whatever value they want to have, but the first 4 bits should always be 1110, which means the range for this IP address is it starts from 224.0.0.0, which is pretty much 1110.0.0.0, then another 80.80.80. Like this pretty much translates to 224.0.0.0 in decimal to something called like 1110.1111, then 81.81.81, which basically translates to 239.255.255.255. Right, so this is your range, and well, as with other classes and other stuff in networking, you cannot use all of the addresses. There are few addresses which are reserved for various purposes. So for example, the address 224.0.0.1, just an example, 224.0.0.1, this is the all host group, which means it will send whatever message you send at this IP, it will be sent to all the pretty much all the hosts on that network. So this entire multicast thing, you can draw some analogy to radio, right, and radio frequencies. If your radio device is tuned to a particular frequency, anything that happens on that particular frequency, in radio world we call it broadcast, but if you just draw an analogy, it's like whatever comes at that particular frequency, whatever is broadcasted at that particular frequency, only the devices tuned to that particular frequency will get it, right? It's not that a device can by default listen to all the frequencies. It can, but first you need to tune your radio device to that particular frequency. So it's to some extent similar to that. It's a subscription model. Okay, so now we know what are multicast groups and what are multicast group addresses. The other thing we need to understand is that not all routers are multicast routing capable, right? Because at the end of the day, like, it doesn't matter if your host is capable of receiving multicast datagrams if your router doesn't support multicast routing, or it doesn't support multicast datagrams, right? So for multicast to work end to end, your routers also needs to support this multicast routing and multicast datagrams. So for example, if I have a simple network where there is a router R and there is a node N1 and it's connected to N2 and it's connected to N2, N3 and N4, then, and let's say N1, N2, N3 all want to do multicast communication among themselves, there are multiple groups or things like that, R needs to support multicasting in the first place, right? Now it's a very simple network. In this case, it's a local network with one router and there are 4 nodes, right? Things become more interesting when, let's say, where we have a topology like this. There is N1, we have got a router R, N1 is connected to R is connected to, let's say this is R1, this is R2, and then R1 is connected to N2, R3 is connected to N3, N4, again R1 is connected to, let's say, R3. I'm just drawing this from my mind, it's just a simple example. It's connected to N5 and things like that. So what I'm trying to say is that, let's say this is a multi-router network where messages or datagrams are being passed or forwarded across routers. In a case like this, in a situation like this, where let's say all the nodes connected to a router is forming a separate subnet, all the intermediate routers, let's say there exists a multicast group where N5 has subscribed, N3 has subscribed, and N4 has subscribed. So let's say this is forming a multicast group. So if now N1 wants to send a datagram to such a multicast group across N4, N3 and N5, the first thing that has to be supported is both R1 and R3. Not only just R1 and R3, but R1, R3 and R2. All of them must support multicast routing among themselves, right? So R1, R3 and R2 should be aware of multicast. They should be multicast aware. They should know how to forward multicast packets, multicast datagrams. And not only that, they should have some multicast routing algorithm going among themselves. So there are a number of multicast routing algorithms, and I won't go into those because each of those might want a separate video on themselves. But some of the popular multicast routing algorithms are DVMRP, which stands for Distance Vector Multicast Routing Protocol. There is PIM, Protocol Independent Multicast. These are the some of the various multicast routing protocols in picture. But again, let's not go into those. So yeah, this is something we need to be aware of if we are doing multicasting, if we are planning to do multicasting, and also your kernel should be, like your Linux kernel should be compiled with the multicasting option switched on. So most of the modern recent kernel versions come with multicasting capabilities turned on or switched on out of the box. You do not have to decompile your kernel, which is a good thing. For example, the operating system that I'm using right now is Ubuntu, and Ubuntu comes with multicasting enabled in the kernel. Okay, so now the immediate next question is how does a host show its interest in joining a particular multicast group, or rather how a number of hosts join a given multicast group? There's a immediate next logical question that should come to our mind. So let's find out how that happens. So for that, socket options is our friend, which is basically the sockopt system call. Since joining a multicast group is nothing but setting a option on the socket. So let's see how it can be done. So creating a socket to perform multicasting I'm talking about right now I'm talking from the transmitter node point of view, like the node or the client which is actually trying to transmit some multicast datagram to a group. So to create a socket which wants to send out some multicast message is nothing different from creating a normal UDP socket. So you first pretty much create a socket, like it's just pseudocode. You just first create a socket for UDP, basically a datagram socket, right? Once you have this datagram socket, the other thing you need to do is you need to create a sock addr-n. I hope I got the spelling correct. I mean the struct name correct. And this has to be the group address and group, let's call it group addr. So the family would obviously be inet, since you are doing a internet type message transmission. Here you need to specify the group address. So just like a not usual socket addr in struct, it will take a internet IP address as well. And in this case, the IP address would be the multicast IP, right? Not the IP of any host, but the multicast IP. And of course, it will take a port. So the port is a bit important, like at the receiving end, at the receiver end, your client should bind to this particular port, right? Because the port that you specify here while sending out the multicast message is the same port where the multicast message would be sent at the receiver end, right? So at the receiver end, you can bind your process to IDDR any, which is 0.0.0.0, all interfaces. However, for port, you need to bind it to the port which you are specifying at the transmitter end. So once you have got the group ADDR set up and you have got the socket created, the first socket option you need to set is the so first let me complete the transmitter side completely, and then I'll say how a receiver can show its interest in a particular group, or how it can join a particular group. So at the transmitter side, you have got the group ADDR setup, you have got the socket setup, and that's pretty much it. Now all you have to do is you need to send your message or transmit your UDP datagram at this particular group address, right? And that's largely it. So the two other socket options at the transmitter side that you need to set on this sock are IP multicast IF, which tells the kernel which interface, if your machine, if the sender has got multiple interfaces, then which interface to choose while sending out the multicast datagram, right? And a given socket can only be associated with one interface when it's sending out multicast datagram. So if you think that your host is connected to multiple networks, and that is multiple networks via multiple interfaces, and you want to do a multicast to all the networks or all the different networks your host is connected to, you cannot do it with the same socket, right? In that case, you will have to create a different socket. So one socket can be associated with only one interface for sending out multicast datagrams, and that can be done with IP multicast IF. Let me write it down. IP multicast IF. So this is one. The other socket option that you would want to care about is, so this is one, and the other one is IP multicast TTL. As the name suggests, it sets a TTL on the outgoing multicast datagram so that network loops can be avoided. So if a datagram for some reason is going in circles, we know that whenever it crosses a router, well, in our simple case, we have only one router, that is my home router. Like I'm also using the same host, like I'm not even using a separate host for this exercise. But in a real world scenario, when you have multiple multicast routers in picture and the packet is being forwarded, the datagram is, I keep saying packet, but in UDP world it's all datagram. Again, people use interchangeably datagram and packet, but anyways, so the datagram might be forwarded across multiple routers, and in case if the datagram is lost and it goes in circles, each router usually subtracts one from the TTL, and the last router which sees that the TTL is 0, it would discard it. So it prevents the usual classic loop case, this TTL parameter. Not only this parameter prevents your datagram to go into a loop, not only handles looping situations, but it also marks something as a multicast threshold. Multicast threshold is a parameter or a setting which is present at the multicast router level. The multicast threshold of a router determines what is the number of router forwardings that multicast router will allow for a given datagram, right? So if I just try to rephrase it, the multicast threshold of a router determines that for every datagram that reaches that router, how many future router forwards it can allow for that particular datagram. So let's say if the multicast threshold of a router is 5, it means that after a datagram passes that router, it can only be forwarded at max 5 times, because every router will be subtracting 1, right? The significance of this is a multicast router can be configured to drop datagram whose TTL is greater than the multicast threshold of that particular router. So if the remaining TTL of a multicast datagram is, let's say, 10, and the multicast threshold of a particular router is 5, then when that 10 TTL datagram reaches the 5 threshold router, it will simply drop that datagram, right? So this is multicast threshold based filtering. That purpose is also served by this IP multicast TTL. Okay, so now let's come to the receiving side of the things, right? Even for receiving, we need a UDP socket. So it's pretty much again as simple as creating a UDP socket. So it's a datagram type socket, and this time, like the sock ADDR in address you will be using to bind the listening process to, it will not contain any mentioning of the group IP address, but it can be any IP address present on that particular host, like any IP address belonging to one of the interfaces present in the host. You can also do IDDR any, because just like any other normal listening process, the IP will be sent to that particular IP at which the process is listening, right? And it has got, like, the interface at which the packet is coming has got nothing to do with whether it's a multicasted packet or not. Once the datagram has reached the host, is just another UDP datagram, right? The fact that any datagram meant for that particular group will also be forwarded to this particular host, that's where multicasting comes into picture. But how the packet is actually delivered to the host is just like any UDP packet. So for any UDP packet, the process has to listen to a local interface IP, right? For that, socket ADDR_IN for this particular struct. To keep things simple, you can simply use IDDR any 0.0.0.0. That is, you are listening on pretty much all the interface for the multicast packet, for the multicast datagram, and the port would be the same port that you used here, which I just mentioned a while back. So the port that you created while creating the socket ADDR in at the transmitter end, that same port you will have to use at the transmitter end, or rather the transmitter will be listening on this port, right? And once you have done that, the next thing that you need to do is use another socket option on this UDP socket, and that socket option is called IP add membership. And this socket option, well, the purpose of this socket option is already very much implied from the name of the option, that it makes the host a member of a particular group, but the value that it takes is of the form is a struct which goes by the name IP_mrec. It takes two members. One is IMR multi ADDR. As the name suggests, it's nothing but the IP of the group to which you want to subscribe. So it's pretty much the multicast group IP address. The other parameter or member that this struct has is something called IMR_interface. And this is the interface where the multicasted datagram would be received, right? So it pretty much tells the kernel this socket wants to subscribe itself to this particular group and on this particular interface, right? So these are the two members that IP_mrec takes, and this is the overall set of parameters that IP add membership uses to subscribe a given host or a given host socket to a particular group or groups. So again, you can make a socket a part of multiple multicast groups, right? So all you need to do is set this IP add membership socket option multiple times on the same socket, right? So for example, if you want to subscribe to another group, all you need to do is just call the sock opt once again with IP add membership and use the new group address in IMR multi ADDR parameter, right? That way you can subscribe to multiple groups using the same socket. Not only that, you can subscribe to the same group on multiple interfaces on your host using IP add membership. All you need to do is keep the group address same, the multicast group address same, but change the interface, right? That way you can receive the multicasted datagrams for the same group on multiple interfaces, right? If you have set IDDR any when you were setting up your bind address. So yeah, that's how you can pretty much set up your receiving client or your receiving node for multicast datagrams, and it's pretty easy. And one other thing that we need to know now, perhaps it is not that important when you are writing your multicast applications. When you use this socket option, how does the kernel tell the router, the router to which your host is attached, that your host wants to subscribe to a particular group? How does that happen? So that follows a particular protocol, and it's called IGMP, Internet Group Message Protocol. Using this IGMP protocol, the kernel or your host tells your local router, in my case the home router, that hey, I am interested in this particular group, please subscribe me to this particular group, which means the router makes a note that whenever it gets a multicast datagram for that particular group, it will first check what are the hosts that's present in its local network that's subscribed to that particular group, and if it finds such host, it will forward the datagram to those particular hosts. That's the protocol that's followed, and that's called IGMP. Now there is a very inherent problem with this IGMP protocol and this method overall, and if you can guess what's the problem I'm going to talk about, do comment it below in the comment section. But it's a pretty critical problem that's present with this approach. For example, let's say we have a node n1, it's connected to a router, and it's connected to n2, n3. Now the fun part is, instead of, now this router is also connected to other router, other networks, which is fine. Now instead of being connected to another router or another node, this time it's connected to a switch, a L2 switch, not a L3 router but an L2 switch. And again, let's say it is connected to some nodes, N4, N5, and let's say this is again connected to a router, and that is again connected to, let's say, N7, N8. A very imaginary setup, but it can be very well a case, right? Now the switch can be connected to anywhere, like the switch can be connected to more number of nodes as well, right? Now let's say in this case N4 wants to do a multicast transmission, a multicast datagram, and let's say the group is N1, N2, and N3. This is the group, right? So N4 wants to do a multicast datagram to this group comprising of N1, N3, and N2, which means N1, N2, N3 must have invoked the IP add membership socket option on this particular whatever the group IP is. So now N1, N3, and N2 are part of that particular multicast group, and N4 knows about it, and N4 wants to send some data to that particular multicast group. So problem here is IGMP is a L3 protocol. It's not an L2 protocol, right? Now N4, when it will do the multicast, the first hop is the switch, which is a L2 device. It cannot process L3 algorithms and L3 protocols, right? And as I mentioned, IGMP is a L3, is a network layer protocol. So how does this work? So in this case, what has been done, and what has been done very cleverly, the switches have an extension or a feature which is called IGMP Snooping. So what's IGMP snooping is, whenever this router gets a multicast group membership request, right, or any multicast protocol request, like membership request, there is a membership deletion or a membership withdrawal socket option as well. Any kind of, if the router receives any kind of such multicast protocol related IGMP protocol related request, this switch will use this method of IGMP snooping to snoop that information, so that it also knows that what is the multicast group address to which N1, N3, and N2 is subscribed to. That way the switch can also be a part of the multicast routing. Just imagine, the switch has got no idea of how to process IGMP protocol, because IGMP is a L3 protocol, not an L2 protocol. But using IGMP snooping, the switch can extract information from the router, only the amount of information it needs to participate in the multicast routing and to forward the respective multicast datagrams, and it will participate in the multicast process. So it's very important, IGMP snooping. Without IGMP snooping, switches in the network would render multicast routing useless, because switches cannot process IGMP original protocol. So that's also something very interesting and something which is worth knowing in the entire grand process of how multicasting works. So now we know how to set up a multicast group, how to transmit multicast datagrams, how to receive multicast datagrams, and all those kind of things, how multicasting works, what is IGMP, what is IGMP snooping, and all these kind of things. So next, let's see this entire thing in practice. Let's see how we can actually send multicast datagram from a C program, and how a few C processes can receive those multicast datagrams. Okay, so here I have a simple server.c and a client.c, and this server.c will be transmitting multicast datagrams at a particular group IP address, and the client will simply try to receive those multicasted datagrams at the decided port, right? So let's go over this server. It's a pretty simple server, and again, the socket that we'll be creating is there is not much of a difference between a multicast socket and a UDP socket because they are the same. So yeah, so the first thing I do is I create a UDP socket, a datagram socket, and then I instantiate a socket dir in struct, and I call it group sock because it's for tracking the group IP address. And then the first thing I do is I make the family as AF-INET because it's an internet family socket, and the address where I want to send the data is the group socket address, right? And for this purpose, for this example, the group IP I have chosen is 230.1.1.1. Remember, it can be anything between 224.0.0.0 to 239.1.1.1, right? Okay, and the port I have chosen is 4321. HTONS is simply host to network byte order conversion for short. Now remember, the other thing that we need to do is call the sockopt with the IP multicast IF option, which pretty much tells the kernel which interface to choose while sending out or transmitting the datagrams, the multicast datagrams. And for this, I have chosen this one. So if I show my terminal, so if I do a IPA, you'll see this is the only interface I have. So there'll be a tiny correction. It will be 57 and not 58. Okay, I simply mentioned the address of the interface through which I want to make the egress, that is the transmission of the multicast datagrams. The other option, socket option I'll be using is the IP multicast TTL, and the TTL I'll be setting is 1 since there is only one hop, right? There is no router hopping happening over here, so TTL of 1 is totally fine. And finally, in a while loop, I start transmitting the messages to the group socket IP, and the message I am transmitting is simply something like this is a multicast message 1, 2, 3, 4, and continuously I'll be sending in a loop with an index which will differentiate the multiple messages. So that's our server. Let's check if the server compiles. Let's compile the server -o server. Let me just zoom in a bit more. Server.c. It compiled. Let's see if it runs. Yep, as you can see, it's running. It has started transmitting the messages to the group IP address, that is 230.1.1.1. However, we do not have any receiver at this point of time, so it's just simply saying that the message is being transmitted, but no one to receive as of now. So let's check our client now. Again, the client is also pretty simple, and the first thing we do is we create a UDP datagram socket as just like the server. Now, since I'm using the same host for testing both my clients, or it doesn't matter how many number of, again, before I go over here, like the client and server definitions are a bit sloppy over here. I am calling this server just simply because it is the one that's transmitting the message, right? And I'm calling this a client because there is a one that's receiving, like it's a client of the server who's transmitting the messages. But usually what happens is it's a server process that actually listens on an IPN port, but here it's completely the opposite. The server or our transmitter, it's not listening on any IPN port, right? It's not binding to any IPN port. It's not listening to any IP or port because it's a UDP socket, and all the server needs to do is transmit the datagrams at a particular group IP address. That's it. Conversely, the client needs to bind to a particular IPN port because UDP allows a socket to be bound to an IPN port, so that we can easily read from that socket which is bound to that particular IPN port, right? So it's just a convenience that UDP sockets provide us, that we can bind the socket to a particular IPN port to let the kernel know from which IPN port we want to read our messages, right? In this case, the server is not the one that's binding to a IPN port, but it's actually the client, the receiver, right? So I just wanted to make sure we do not have any confusion related to that. You can always bind a UDP socket to an IP port, doesn't matter if it's a server or it's a client. Okay, so the first thing we did is we created the socket, which is a datagram type socket. The next thing we did is we used a socket option with SODUs port. And why we used SODUs port here? Remember, like our host is same. In order to simulate this example, I will be running multiple receivers or receiving client on the same host, right? And also they need to run on the same port because that port needs to match with the port at which the server is, the transmitter is transmitting the messages at. So again, we have the same thing just like my last video, wherein we need multiple processes to bind to the same IPN port. right? It's only that this time the traffic won't be load balanced between those multiple processes, but all the processes will receive exactly the same data because of the nature of the datagram, because it's multicast, right? Since multiple processes needs to bind and listen at the same IPN port, we need to use SODUs port in this case. Okay, so yeah, we enable SODUs port, and the next thing we do is we set up our local address. Why we need the local address? Because this is the address to which we are going to bind our socket. Again, the type will be a FINET, port has to be 4321, and the address, the SADDR parameter can be anything. So I'm just using INADDR any, right? It's pretty much 0.0.0.0. It will bind to all the interfaces on the same port 4321. So next I do the bind call, and then now comes the multicast related parameters or socket options. The first thing I'm going to do is I want to let the kernel and the router know that this receiver is interested to become a member of the group 230.1.1.1. And how do I do that? Using the IP add membership. So all it wants is a parameter of the type IPMREC, which I just mentioned. IPMREC needs two fields, two members. One is the actual group IP address, which is 230.1.1.1, and the interface on which it wants to receive that multicast datagrams. So again, I'll make a small correction here. It will be .57. So I've mentioned the interface as well, and now I simply call set sockopt with IP add membership option, and I pass the group variable or the group parameter which contains the multicast IP and interface details, right? So post this, now my receiver is a member of 230.1.1.1 multicast group, right? And after that, it's pretty simple. We just go into a while loop and we start reading from the socket. Whatever we read on this socket, we simply print it to STD output, right? So first we bind to the local address, then we declare our desire to be a part of this multicast group, and then we simply start reading from the socket and writing to STD output, right? So let's see how it looks in practice. So first let's compile the client once again, right? Both of them are now compiled, and now what I'll do is I'll once again I'll zoom out this a little bit, and once again I'll do a split vertical. You know what, let's make another terminal. Okay, zoom this a bit. So this time what I'm going to do is first I'm going to start the clients. This is one client, so it says that socket is attached to the interface, and now it has joined the multicast group as well. So now it's pretty much waiting. So basically it's waiting at the read call on socket, which is a blocking call. Another one and another one, and now let's start the server. Now look at that. So now as you can see, all the messages that the transmitter is transmitting, you can check them by the index numbers. Each and every of those messages being received by all the three different clients at the same time. So the transmitter is transmitting only once. It's not transmitting three times because there are three clients or three receivers. It's transmitting only once, and all the three receivers are receiving at the same time, right? And the fun part is, let's say I now bring in another client. What happens then? It starts receiving from the exact same state, right? So right now the 48th was the latest one when this fourth client came up, and it started receiving from the 48th message. So multiple servers or multiple transmitters can transmit to the same group, right? So let's try that once as well. So what I'll do here is I'll kill this. I will open the server and just I'll recompile this server on the fly with a different message. So what I'll do is I'll say this is a multicast message from server 2, and let's see what happens now. Let's start this server as well, or this transmitter as well, and look at this. So what it pretty much says is that this is a multicast message from, so now the clients are getting messages from the multicast datagrams from both the servers. So, and it's getting alternatively. I'm getting both this one from server 2 as well as from the original server, like both the new server 2 transmitter and the original server transmitter. So the number of the transmitters doesn't matter. Any number of node or program can transmit to a given group, and any number of clients or receivers that are interested in receiving datagrams from that particular multicast group can do so by becoming a member of that group, right? So at this point, what I could have also done is bring in another device, connect to this network, my local home router, and transfer this client program or the receiver program to the new device and start it. If I execute the program in that machine as well, it will also start getting the same message, right? It will also start getting the same datagram. If I just now close this, because it's really becoming difficult to read, it's back to reading just only from receiving messages from only the transmitter 1 or server 1. This is what I wanted to discuss in this video, right? I wanted to discuss about multicast, how you can send the same datagram or same message to multiple clients at the same time without doing it individually or in separate processes. How you can send datagrams to multiple clients who are interested in, as I mentioned, interested is the key word here, which differentiates broadcasting from multicasting. So yeah, I wanted to discuss how clients which are interested in receiving messages from a multicast group can do so, and selectively, and how program can send multicast datagrams to a given multicast group. So yeah, do let me know in the comment section if you have ever used multicast, or if you are using multicast actively in your work or in your side projects, and how you are using it, how it's helping you. That's it for this video, and I hope you all liked this video, enjoyed this video, and see you all next time.